Welcome back, everyone. Today we're gonna do a little bit of a different video. Thought I would do a draw my life style kind of thing. See what works, see what doesn't work. Just give it a go. Hope you enjoy. All right, ladies and gents. So today we are talking about quantum entanglement. So first off, we have to explain quantum states and spin. So basically, spin is an intrinsic, or natural, form of angular momentum of elementary particles. No, not elementary as in my good friend Sherlock. Elementary refers to particles that we have not been able to subdivide any further, and do not know if they are composed of smaller particles. This spin is what is responsible for the magnetic properties of the subatomic particles. Electromagnetism is generated by moving charges. Now, it is important to note that these particles do not physically rotate around an axis. This is quite misleading and is just a result from outdated nomenclature contradicted by modern research. So what then actually creates the magnetic properties of these non-rotating charges? Well, spin. I know, we just looped back on ourselves, but that is the property we explain it with. These particles have a magnetic dipole, meaning that there tends to be two differentiated sides, but do not generate that dipole property by physically spinning on an axis. Spin is a very hard thing to tackle conceptually, especially because of what comes next: entanglement. So as it stands, each electron on its own has a spin state. This spin state, however, is not set in stone. We can only measure the spin of a particle in one direction at a time via a detector. We have two different possible outcomes after detection: spin up and spin down. We are not able to tell, though, if the up or down state we measured is exactly up, exactly down, or actually at an angle. We only know what general direction, determined by the axis of detection, the spin state is. We detect the spin state on a certain axis now, and we know, based on our observation, that the spin state recorded holds true for that axis of detection, no matter how many times we record it. However, when we try to detect the spin state in another axis, the record of the first axis becomes nullified, and there holds again no definite result of what that initial spin state could now be. We can measure the x spin state, but not know the y or z. Then we can measure the y spin state, but we lose our certainty of the x direction again. It's almost as if, the moment we look away, it fights back. Our observation changes the outcome of the spin state. Now on to entanglement, for real this time. When two electrons are entangled, it means that they hold certain properties based on the properties of the other. So for instance, if I have two electrons unentangled, they each have the possible up or down spin state to possibly be. When they are entangled, however, the possible spin states become intertwined. It turns out that these particles will have opposite spin states when measured on the same axis. For example, let's say you and I are electrons. We each have a bag with two marbles in it. One marble is green and the other is red. It doesn't matter what marble I blindly pull out. It shouldn't affect which one you do. However, this all changes when we are entangled. To make this example work, I take your bag of marbles and put them away. Now, we each pick from my bag. I blindly pick the green one, leaving you to pick now. There's only one outcome for you to choose, the red marble. My result affected your result, and through entanglement, our outcomes have led to opposite states. Getting back to actual entangled electrons, they are opposite along the same axis due to the law of conservation of angular momentum. Now, these particles can get entangled through interaction with other quantum systems, but they can and will retain that entanglement over long distances if given the space to separate. This means that quantum systems could end up light years apart, but still be entangled. Einstein wondered about this phenomenon, not adhering to common initial theories that it is a sort of communication between the two particles. He proposed instead, since nothing travels faster than light, and since this communication of sorts seemed to defy that logic, that the particles seem to innately contain this hidden information of sorts. This hidden information would be a roadmap, basically, of spin states, a predetermined set of orientations. I guess something I could liken this to would be DNA. We have a code in each of our cells that dictates what the cells should be and do. Anyways, both of these theories are still up for debate, and the battle is not over just yet. The applications of entanglement are exciting and vast, but that, my friends, is for another video. I hope to see you all next time. Links to my Twitter and blog are in the description. Thanks for watching.